says 3 identical thin bars, length L and mass M, are assembled into 3 sides of a square and suspended from a comparatively mattress forked rod, also of length L. Shown below. The whole thing is set in motion so that it swings in the plane of the page and remains rigid with the original shape. On the sketch, indicate your choice of Cartesian and generalized coordinates. Right, so let's draw the system down. Right. How many degrees of freedom does the system have? Right, so 1 degree of freedom can only rotate. It cannot bend or doesn't have any hinges. This whole thing rotates, and there's no other stuff going on. Right, what about the generalized coordinate? The angle, theta. This is all stuff we're quite comfortable with and familiar with. Choose your choice of Cartesian and generalized coordinates. Now when we say Cartesian and generalized coordinates, I mean that as well as producing theta, we also should produce Cartesian coordinates in which to express everything. So we normally choose x to go across and y to go upwards. Although sometimes we choose x going down and y going across. That's absolutely up to you, as long as when you choose your coordinates, you are consistent. So whatever coordinates you draw on this picture, you keep. And you work with them consistently, you will then get the same answer. Right, so on a sketch, indicate your choice of Cartesian and generalized coordinates. Use an angle generalized coordinate. There they are. Cartesian, Cartesian, generalized. So that's question 1. Calculate the position of the center of mass of the 3 bars taken as a single object. Indicate on a sketch where the center of mass lies in relation to the 3 bars. So we guess that it's going to be somewhere here. But now we should calculate it. And what we can do is we can take the system of 3 bars and consider it separately in order to compute the center of mass. And for this problem, I'm going to use a result which I am very fond of. I am very fond of this result. I like it. I like to write it down when I am staying up at night making exams. Right. A result that says, when I have the center of mass of a system of different components, doesn't matter what the components are, let's call them A, B, C, D, right? And for each one, there is a center of mass. For each one, there is a center of mass. Let's call it A bar is the center of mass of that one, B bar is the center of mass of region B, C bar is the center of mass of region C, D bar is the center of mass of region D. Then, the mass of the whole system times by the center of mass of the whole system. If I call the whole system S, say, the mass of S times the center of mass of S, my whole system, S being equal to, let me be clear, A union B, union C, union D, right? Then the mass of S times the center of mass of S is going to be equal to the mass of A times the center of mass of A, plus the mass of B times the center of mass of B, plus the mass of C times the center of mass of C, plus the mass of B times the center of mass of D. Right, this is for 4 things, but it's quite clear that this works for any number of things. In other words, if S was the sum over all regions A, sub I, then I could write MSS is equal to the sum of MIA sub I. Right? If S was, in this case, equal to the union over I of A sub I. Right, so it doesn't matter how many little components I divide my system into. I can get the center of mass of my system by adding up the weighted average of the center of mass of each little subcomponent. And it would be a good plan for you to figure out how to prove this. In particular, in your tutorial, we showed, well, this result was proven for the following, when it's just A and B. So it was just this result. MSS bar is equal to MAA bar plus B bar when X is just a union of A and B. Right. But it's true for anything. It's true when you break your system up into any number of components, you can just perform the sum to get the center of mass of the whole system. I'm not going to prove it now, I want you to think about it. But let's look at this particular tutorial problem. Why don't we just do that? Why is that bother? Can you see three distinct pieces to this object? Right. So let's call this one A, let's call this one B, and let's call this one C. Then we have a formula now for computing the center of mass. These rods have equal mass, they have equal length. The length of each rod is L, and the mass of each rod is M. Where is the center of mass of the uniform rod? It's the middle of the rod. We don't have to perform an integral to know that. The middle of the rod. There's the center of mass, there's the center of mass, there's the center of mass. We can now use our little formula to compute the center of mass of the whole system. The mass of the system times by the center of mass of the system is going to be the mass of A times the center of mass of A plus the mass of B times the center of mass of B plus the mass of C times the center of mass of C. In order to compute this value, we should produce some coordinates or other in which to do it. So, well, I'm going to put a coordinate system here with the y-axis going up there and the x-axis going across there. Right. In this coordinate system, what are the coordinates of the A center of mass? Anyone want to hazard a guess? I have to move to the left half a rod length and then up half a rod length. So what is that? Minus L over 2 and L over 2. And this one will be L over 2, L over 2. Right. So, the mass of the system is just 3 times the mass of one rod, since there are 3 rods in the system. 3m times S bar is equal to, the mass of A is just m, times by the A center of mass, minus L over 2, L over 2, plus the mass of B is m, times the B center of mass, which is at 0, 0, in our coordinate system, plus the mass of the third one, which is just m, times the C center of mass, which is L over 2, L over 2. And the sum is equal to m times minus L over 2 plus m times 0 plus m times L over 2, well that's 0. M times L over 2 plus m times 0 plus m times L over 2, that's m times L. So that's 3m times S bar is equal to mL and 0. Therefore, the center of mass of the system is at 0 and a third. Wait a second. I should be writing by 3m, not just by 3. And then the m goes away as well. 1/3 L up and 0. So that's very clearly indicatable now on the drawing. If we go up 1/3 of the way, so let's divide this into thirds, it looks something like that. And if we go up 1/3 of the way, we hit the center of mass. So it's right in the middle of this object and 1/3 of the way up. We can now see that my guess, the little star here, seems pretty much to be exactly where it is. Let me go a bit far along. Right, so that's your center of mass. If you were to draw a little thing here saying 1/3 L, you justify it. Right, so
there, which type did you say proves that the nice result of this?
the nice result was in an early tutorial. Let me see, it was tutorial 615, page 26, tutorial 15, question 1. For 2 objects. And you generalize it to n objects so that you can do it like we did here for 3 objects. And then we don't need to do any integration. Which is nice. Right. Now, let's carry on with this question. We now have question 3. Calculate the gravitational potential energy as a function of the generalized coordinate. Well, that's easy. Because we have computed the center of mass. And the center of mass is a very important point. Because as soon as we know what it is, we can compute the potential energy by simply working out what the object would do if there was a single point acting at the center of mass of its full mass. Now, it's very important to go through all the steps. So, the coordinates of the center of mass, let's work them out. The x-coordinate at the center of mass. What's the radius of the center of mass, firstly? What's the radius of the center of mass? The radius from the center outwards to the center of mass, we can just extend this line, and you can see that we go an extra 1/3 L outwards. Now this little rod here, we were told in the question, has length L. So the radius of the center of mass is just 4/3 L. Which means that the x component of the center of mass, now we know how to do this, we solve pendulum transformation equations in our sleep by now. 4/3 L sine theta, and the y coordinate of the center of mass is minus 4/3 L cos theta. Now that we have these coordinates, it's very easy for us to compute stuff like potential energy, because we can simply write U is equal to mass of the whole object plus, well, I'm calling my object S, so let me be consistent. Mass of the whole system times G times the height of the center of mass, which in my case is the y coordinate of the center of mass, because I chose the y-axis to be pointing upwards. If I'd chosen the y-axis to be pointing downwards, I'd have to put a negative in here. If I'd chosen the y-axis to be pointing to the left, I'd have to be putting an x-coordinate in here. The point is that I've chosen a reference position, a reference height, where I drew this line. And the distance above or below that reference height is the thing that I need to put over here. In my case, the y-coordinate, which increases when I go up and decreases when I go down. It's very important that your potential energy should increase when you go up and decrease when you go down. You have a lot of potential energy when you're standing in a chair, because you can jump. I have no potential energy now that I'm not on the chair, because I can't jump off it anymore. Can't go any further down. So, it's important that whatever coordinates I choose for my potential energy, they increase when I go upwards. It doesn't matter if it's positive or negative. Someone asked me, what's the significance of potential energy? Doesn't matter what's the significance of it, whether it's positive or negative. There is no significance. I can add an arbitrary constant to it. But it is significant that it goes up when I move upwards. and that it goes down when I move downwards, in the case of gravitational potential energies. As I add energy to the system, it must increase. Right. So this is equal to the mass of the system. In this case, there are 3 rods that are heavy in the system. It's 3m times by g times by ycm, which in my case is minus 4/3 L cos theta. So in summary, minus 4 mg L cos theta. Rightio. And now we must calculate the moment of inertia of a single bar if it is rotated around an axis passing through the center of mass of the bar. Simply recalling the answer is not enough. We must show the calculation. Moment of inertia of a bar. We've done this in class. A single bar, when it's rotated around an axis through its center of mass, we are told, and perpendicular to the bar. That's this axis over here. So we're simply going to take the bar and integrate from here to here, from minus O over 2 L over 2 of the perpendicular distance to my axis at each point. So the inertia is equal to the center of mass, the integral of r per squared dm, which is equal to, in this particular case, we are integrating from minus L over 2 to L over 2. The thing we're integrating is some radial parameter, which in fact is r squared. Let's call it r squared times dm, and dm is going to be rho dr, where rho is now a line density. Some people use lambda for line density, alpha for area density, and rho for volume density. As far as I'm concerned, you can use any parameter you like, as long as you know what it means. Rho in this case is a line density. In other words, it stands for mass per unit length. Whereas when it's a volume, it's mass per unit volume. When it's an area, it's mass per unit area. Since we're working with a essentially one-dimensional object here, we're interested in mass per unit length. Alright, so this thing here, mass per unit length, we can compute it either way if we wanted to work out the whole mass of the object. That's the integral of dm, which is going to be the integral over the same parameters, as always the same one, from minus L over 2 to L over 2 of rho dr, which is going to be equal to rho r between minus L over 2 and L over 2, which is equal to rho L, which implies that rho is equal to m over L, something we could have figured out intuitively as well, because when we say mass per unit length over a uniform rod, that's mass per length of the rod, which is a constant. Right, so we can write this out as the rho can come out, m over L, this becomes r cubed over 3, evaluated between minus L over 2 and L over 2. That gives us an answer of 1/3, 1/3 of m times L cubed over, so that's L cubed over 2 to the cube, which is 8, minus minus is plus. Right, and so when we put it all together, we get 1/12 mL squared. And that is the moment of inertia of the rod when rotated through its center of mass. Now we are on to the next question. State the parallel translation of axis theorem. Oh, that's kind. Stating a theorem like this. Well, you won't get that in your exam. But if you state the parallel translation of axis theorem, what does it say? It says when an object is rotated, I don't know, it says something like this, don't copy this down, through an axis. I mean, you can write this in so many different ways. I don't want you guys to go memorizing definitions now. Through an axis at point P that is parallel to an axis at the center of mass where the inertia is known to be IM, then I, the distance d is equal to IM plus the mass of the object times d squared. If we draw a picture, there's your point P, there's your center of mass. What's the moral of the story here? If I'm shifting my axis parallel to my previous axis and I shift it by a distance d, then the inertia gets shifted by md squared. This should tell you, and here's the kind of thing that I can ask, a much more interesting and insightful question than state the parallel translation of axis theorem is, for instance, at which point on an object, if I can rotate the object on an axis around any point, which point has got the least rotational inertia? Why? So, I'll say it again. When an object is rotated, choose in a 2D object like this, a point about which to rotate that object, such that the rotational inertia is the least, and explain to me why the rotational inertia is the least at that point. Okay, at the center of mass. I like the first part. The second part was still a bit shaky, but I see what you're getting at. The center of mass is the point in the object with the least rotational inertia. The reason is, at any other point, I can write the rotational inertia like this. M is a positive number, and D is always a positive, well, D squared is always a positive number for anywhere that's not the center of mass. And so the inertia here is always bigger than the inertia there. That's called inference, and that's a much more interesting thing to test than parrot learning. So that's a nice inference to make from the parallel axis theorem, that you have the least resistance to turning an object if you turn it around the center of mass. And that's also got a nice physical application. If I wanted to spin this chair around, I should try to spin it around the center of mass. And that's very easy for me. Whereas if I try to spin it around, oh, that's much more of an effort. Right, it's more resistance, there's more inertia against me turning the chair like this than there is against me turning the chair like this. That's the physical interpretation of that inference made from the parallel translation of axis theorem. Right, anyway, let's not digress too much. We have now stated the parallel translation of axis theorem. Calculate the moment inertia of the whole pendulum when it pivots around the point at which the massless rod is attached to the ceiling. There's a lot of different ways of doing this. Right, there's a lot of different ways of doing this. We may, for instance, wish to add up separate components. Well, there's a lot of different ways of computing the kinetic energy of this thing. The kinetic energy could be computed by considering each of these ones how the center of mass of each rod is moving, added to how the inertia of each one of these things is changing the system. But that's not what we've been asked to do here. What we've been asked to do is to compute the inertia of the whole object as it rotates about the center. Now, if I have the inertia of one piece and the inertia of another piece, what's the total inertia? It's just the sum of the two. Unlike the center of mass, remember that little theorem that we talked about, that little result, that nice little thing that I enjoy writing down. That thing, the center of masses, that shows you how you combine different pieces of the system when you know the center of mass of each piece. So if I have a compound system of different pieces, A, B, and C, and I want the center of mass of the whole thing, I combine the center of masses according to 1 over the total mass times by mass of A times A bar plus mass of B times B bar plus mass of C times C bar, and that will give me the total center of mass. What about moment of inertia? How did they combine? When I know the moment of inertia of 1, 2, and 3 parts of the system, what's the moment of inertia of the whole thing? You just sum them up. Exactly. You just sum them up. But you must be working from the same point. So, if I know the moment of inertia from the same axis, and I'm stressing this because we've worked out to have a moment of inertia around the center of mass axis of each of these things. And we would like to know the moment of inertia from a common axis, not each around a different axis. So, if you know the moment of inertia from some common axis for each of A, B, and C, then the total moment of inertia, this is the total center of mass. The total moment of inertia of the system is going to be just the moment of inertia for each one. So we can do that, but we need to be working from a common point. From a common point for each one of them. So let's work from this point. It's a good point to work from because if we work from this point, which is fixed and the whole thing is rotating around this point, then we won't need to worry about any translating components of the system, right? So the kinetic energy will be very simple if we calculate all the moments of inertia around that point. If instead we decided, let's be fancy and calculate the moment of inertia as it rotates around the center of mass, that's also okay. We could do that. Then the kinetic energy would be the moment of inertia from here to everywhere, plus the velocity squared times by the mass of the system of that center of mass. Right. Those are the only two options you have. I must emphasize this. I've emphasized it a couple of times, but they are the only two options that you have. Either some point in your system, which may or may not be actually inside the objects of your system. In this case, it's not. It's over here. Either some point is fixed and you're rotating the whole system around that point, in which case you can work out the inertia at that point, and the kinetic energy is simply a half I omega squared. Or maybe there is no fixed point, or even if there is a fixed point, it doesn't matter. You can always work out the inertia from the center of mass and then add the term to the kinetic energy for the motion of the center of mass. There are no other choices. You can do nothing else. Those are your options. Right.